Hey everyone. So on Friday we talked about two analysis, okay, spectroscopic analysis. The first one was about IHD. Okay, IHD. Okay, and IHD kind of tells you by calculating, of course, it gives you a number, and this number tells you if it has a double bond in this unknown, does it have a triple bond in this unknown, does it have a ring, is it a benzene, stuff like that. So it's a very good way to check to see if you're right. Then we looked at IR. IR is way more special and way more sophisticated by having a graph, and this graph indicates what type of main functional group it has. How do you do that? By looking at the chart that we've mentioned in your data table and looking at the graph in terms of where the peaks are. Okay. Now, so today we're going to look at the third method called HNMR. This is an HNMR machine, okay, HNMR spectrometer. Hooked up to a computer, again, it generates a graph. And this graph tells you something known as hydrogen environment. How many hydrogen environment and what type of hydrogen environment? Hence, hydrogen NMR. Again, we don't have one of these at Millikan. And again, we cannot afford one of these at Millikan. Hey, you never know. Maybe one day you'll play with one of these. Who knows? All right, so HNMR stands for Proton Nuclear Magnetic Resonance Spectroscopy. It really doesn't matter if you know the name or not. All you need to know is what does it do? Well, it tells you what the hydrogen environment of an atom is at. Huh? What do you mean? Well, let's take a look at some examples, okay? Here's methane. And what if you were to put methane in an HNMR, what you're going to get is you're going to get one peak. Why one peak? It's because if you look at these hydrogen, they're really all the same in terms of their environment, right? This hydrogen is connected to this carbon that is connected to 3 other hydrogen. You can say the same thing about this too. You can say the same thing about this too. You can say the same thing about that too. So all 4 of these hydrogen are really all in the same environment. So therefore, if you're looking at this computer, you will get maybe one peak or something like that. Because there's only one environment. Let's take a look at another example. This is ethane. Okay. How many hydrogen environment does this have? Well, let's take a look at this hydrogen. This hydrogen is connected to this carbon that is connected to 2 hydrogen and another carbon. Okay, you can say the same thing about this one. You can say the same thing about this one. Can you say the same thing about this one? Well, let's try. This hydrogen is connected to a carbon that is connected to 2 hydrogen and a carbon. Oh, these are also the same. So again, just one hydrogen environment. And again, just one peak. Well, what about propane? How many different hydrogen environments do you see? Again, look at this hydrogen. This hydrogen is connected to this carbon that is connected to these 2 hydrogen that is connected to a carbon. Okay, these guys are the same. And so will these guys. I can bet you're going to say the same thing. The question is, what about these? Let's circle them for now. Let's circle them in different color. These guys are all the same. And guess what? There are 6 of them. And then there are this guy. There's a reason, of course, I put that in different color. Is because if you look at this hydrogen, it is connected to this carbon that is connected to this hydrogen, 1 hydrogen, and 2 other carbon. oh, this is actually at a different environment. This one will be the same as this environment, so these two are the same, but these two are different from these 6. Okay? So if somebody would ask you, how many different types of hydrogen environment do you see here in propane? And your answer would be 2. If somebody tell you what is the ratio, or they call it integration trace. Okay? The integration trace will be 6 to 2, or 3 to 1. Okay, so that's the basis of HNMR. Now, how this works is extremely complicated. What they're looking at, of course, is these hydrogen under a magnetic field and no magnetic field. Okay, the two will create a difference in terms of energy. This energy creates what we call a chemical shift. The greater the amount of energy, the greater the chemical shift. And this chemical shift is measured in ppm, okay, parts per million. Now, this is important, especially when you're looking at protons under water. Well, where do you find proton in water? Well, you can find lots of it in your cells. So if there's something wrong with your cell, this can be used to detect it. Of course, we're not going to use HNMR to do it. We're going to use something that it's derived from. We call it MRI. So when your doctor asks you to go get an MRI, what they want to see is if there's something wrong with your organs. Okay, because your organ is pretty much made out of lots of water, lots of hydrogen, and there ain't anything wrong with them. That's what they want to see. Okay, well, we're all healthy here, so we don't need to worry about that. So let's take a look at an NMR. Here's an NMR of methanoic acid. Let me draw methanoic acid for you. That is methanoic acid. So if I'm going to ask you, hey, how many hydrogen environment there are in methanoic acid, hopefully you see this guy and this guy being different. So your answer here is 2. Well, this 2 will result in 2 peaks. Each of these peaks represents the hydrogen environment. Cool, huh? Now, this peak is at 8. Around 8, this peak is around 11. All right. How do we know? Is there a chart that we can go by like last time with IR? Of course, absolutely. I think this is page 27 in your IB booklet. I don't remember. But here you'll see all the peaks, chemical shift, for different hydrogen scenario. Now, this page is not very well scanned, but if you were to zoom it out, okay, you'll notice that these H's are in bold, and this type of H environment is based on this peak. So you will, if you're looking at a methyl group type of hydrogen, methyl group hydrogen, you'll see a peak around 0.9 to 1.0. Okay. If you're looking at this hydrogen, which is really a hydrogen part of an ester, hopefully you see that this is an ester, and this carbon is bonded to the carbon that is bonded to double bond O, and an O. So these hydrogen will have a peak at 2 to 2.5. Okay. Versus this one's obviously something representing a ketone. So a hydrogen that is bonded to an H, the hydrogen that is bonded to this carbon that is bonded to a ketone carbon will give you a peak around 2.2 to 2.7. So hopefully you have a data table and you can see the bold H. All right, with this table in mind, let's go back. Whoa, don't want to give you guys the answer all at once. Okay, let's take a look at the NMR again for methanoic acid. Now, we have two peaks, and we know why we have two peaks is because there's two different hydrogen environment. Just represent them with different color. Two different hydrogen environment. Okay, so basically this and this represent these, but which one represents which? Now that's where the graph comes in. Let's take a look at this peak. Peak 11. Okay, so let's take a look at this chart and find 11. Okay, or a range of where it covers 11. Oh, right here, right in our face. Maybe. So right there. Okay, from 9 to 13. So obviously 11 is between. Well, this peak is talking about this hydrogen. Oh, and looks like this hydrogen is part of a carboxyl. Is there a carboxyl here? This is a carboxyl. My goodness. So what that means is that this hydrogen is totally talking about this peak. Or this peak is totally talking about this hydrogen. Right? Hey. By process of elimination, this hydrogen is probably talking about this peak. Or this peak is talking about this hydrogen. Now, the problem with this table is that it doesn't have the information for this hydrogen. They did not take into account the hydrogen for methanoic acid, that is not the acidic part, so they did not have a number here for that hydrogen. But you can pretty much bet if you were to extend this graph, okay, you would say around 8.0, you will have a hydrogen that is based on that, something like that. Okay. Well, it's a shame that they don't have everything, and what do you expect? You can't put everything down, just the important stuff. But that's how you do an NMR, or how to analyze an NMR. NMR. Okay? All right. Hopefully that's clear. I have a couple of questions here. Okay? So I'll do one, and then you do the other. So number one, state how many signals do T-butanol have? T-butanol. Okay, let's draw T-butanol. This is T-butanol. So this is the tert alcohol. Tert butyl alcohol. So, hey, by looking at it, how many signals do you see? Well, I see the fact that these guys are all the same. That's one. This guy is different than these guys. So that's 2. So your answer is 2. There's 2 different hydrogen environment. So you will get 2 peaks or 2 signal. Okay. Now remember we talked about integration trace. Integration trace pretty much just talk about the ratio of these hydrogen. So since there's 2, there's going to be 2 numbers, right? Of course. And what is the ratio of these 2 numbers? Well, this looks like there's 9 of these guys, so it would be 9, 2, 1, because there's only 1 of these guys. All right. So that's how you do integration trace. All right, so maybe we should pause. You guys do the next one, and we'll take it up. All right, sure you guys have already unpaused and figured this out because this stuff is not that hard, I hope. So let me pick another color to use from. So let's take a look. Ooh, an ester. So we have an FN08, methyl FN08. So that's what it looks like. All right, that's pretty cool. So how many different types of hydrogen environment do you see? Well, I hope you don't say one. I really hope you don't say one. Because if you look at this, let me just draw these structurally, even though you guys know I don't like structural formula because it's a lot of work. This is what it looks like structurally. Okay, so if you look at this H right here, that is bonded to this C. This C is bonded to two other C that is bonded to a C. Two H's and a C. This H is bonded to a C that is bonded to two H and an O. Okay. These three are in the same environment. These three are in a different environment, but these three are the same. So your answer again is 2. Okay. What is the ratio? Pretty simple. 3, which talks about these three. 2, these three. So 3 to 3. Nobody present 3 to 3 in a ratio. This is not hockey. That means 1 to 1. Right? So hopefully that's what you got. So that's HNMR. Okay. So that means if you were to put terbutanol in an HNMR, you'll most likely see 2 peaks. And if you put methyl ethanoic in an HNMR, again, you'll see 2 peaks. Okay. Where those peaks are will be based on, of course, what you're talking about. Okay. All right. The last one here. This is the last part of organic spectral analysis. This is called mass spectrometry. Now, whoa, doesn't that sound familiar? Of course it does. The last time we looked at mass spectrometry, we were talking about empirical molecular formula. Okay, and mass spectrometer, which is this guy right here, this is actually called a mass spectrometer mini. Well, more like mass spectrometer portable. Okay, because you can take it everywhere. This is definitely a lot less expensive than the real mass spectrometer that they have in medical labs. What does it do? Yes, what does it do? Well, it analyzes the molar mass of an unknown compound. Okay, because once you know the molar mass, you can use certain mathematical formula to find out what the molecular formula is, given the empirical formula. But that is just an application that we saw before. But the whole idea behind a mass spectrometer is a lot more complicated. And let's take a look at what it really does. So what it does is that it has the ability. So this machine right here. Okay, this machine right here. Again, which we don't have here at Millikan, has the ability to ionize a molecule. Now, not just ionizing it, but also break it apart into fragments. Now that's pretty cool if you think about it. Okay, not only does it, this little thing right here can take a compound and break it into pieces, if you were to think of it that way. Okay, that's pretty crazy if you ask me. So let's take a look at what that means. Okay? Now, you have some sort of molecule. Okay, well, whatever that molecule is. And you're going to ionize it. Okay? By ionizing it, what you're doing is you're actually taking away electrons. Remove electron. So what happens when you remove an electron out of a molecule? Well, this molecule becomes positively charged, right? Now, not only that, but it becomes something called a radical cation. Okay? Radicals are something that is neutral. It does not contain a charge, but at the same time, it has this electron that is kind of right there where it's not being bonded to anybody, and you know that's not normal. Okay? How often do you see things like, let's say for an example, oxygen, okay, like this, okay, methanoic acid. How often do you see this? You don't. You usually see it as a pair. Well, radical will have this as a standalone. Okay? Because of that, this is extremely unstable. So unstable that it's easy to fragment. It breaks apart. It breaks apart to two other molecules. One of them, let's call it M1, will be positively charged. And the other one, which we call M2, is a radical. Okay, so this guy is called a cation fragment, and this is the radical fragment. Now, what you need to know is how it fragments. So when something do fragments, what do you see in terms of the graph that it produces? Yes, it produces another graph, so this is our third graph if you think about it. Okay, now what we're analyzing, of course, in terms of these graphs are mass. So they will look at the mass of this and mass of that. Now, this really doesn't make much sense unless we start looking at one of these. So let's take a look at one of these. So here's a mass spectrometer's output for 1-propanol. This is 1-propanol. And as you can see from the mass spectrometer, there are so many peaks. Well, I can tell you right now, each of these peaks represents a certain fragment, but only some of them are important. Now, which one is most important? Well, for most of you, you would think, of course, this is the most important. The very, very last one. Why? Because the very, very last one indicates the molar mass of your compound. Okay? Because we know, using our skills of calculating molar mass, that propanol is 60 grams per mole. Okay? Hence, your last peak should be 60. And it is. Thank goodness. Imagine if it's not. Okay? But the question is, what are these? Okay? Now, there's a couple of peaks that I'm interested in. Okay? Because these peaks can give me a nice analysis with, of course, my IB unknown booklets in terms of what they are. And that is this peak at 31 and this peak right here at 29. These two are within my interests. Why? Because let me show you something. okay, here's section 28 in your IB booklets. It tells you these things called fragment loss. Now, these are not peaks, okay? Don't think that, oh, CH3 will give you a peak at 15. No. No, don't think that way. What 15 means is that 15 is the mass of CH3. Okay? So if your chemical has a fragment of CH3, the molar mass should lose 15 grams per mole. If your chemical lost a fragment that is OH, it will lose 17 grams per mole. If your fragment lost water, it will lose 18 fragments per mole. Okay? If your fragments takes away this carboxyl group, which is C double bond OOH, you will lose 45 grams per mole. So these are what it lost. They're not peaks. So don't go around saying, oh, I have a CH3. Would I expect a peak at 15? Would I see a peak right there? 15? No, you won't. Because these peaks are actually based on the mass of the molecule. And these peaks are based on the fragments that this broke up to. And it can break up to anything, right? Or break up to anything. So, let's analyze this. Let me put this back up here. 1-propanol. No, what am I doing? Okay. Remember what I said? Today, we are interested in this peak, okay, which is 31, and I'm interested in this peak, that is 29, okay, and let me just tell you why. It's because when this fragmented, what it fragmented to is CH3CH2 and CH2OH. Okay, so when this broke apart, it broke apart to be these two. And these two gave me a very strong signal. Now, we all know what 60 is. Okay, 60 is based on the whole thing. But what is that 31? Well, this 31 is pretty obviously, if there's such a word, this. Okay? This is this. This 29 right here is based on this. If you don't believe me, you can always add this all up and you'll know it is equal to 31. Add this all up and you'll know it equals to 29. Okay? So the whole idea of a mass spectrometer is that it takes a compound and it breaks it into different fragments. Okay? What we're doing is just concentrating in these two fragments to see, of course, that, oh yeah, I know where these two numbers are coming from. This is representing, of course, this fragment. This is representing of this fragment. Okay? Then you maybe want to ask, what about the others? How come we never talk about the others? Let's talk about this guy, 59. Where's this 59 coming from? Okay? Well, 59 maybe is this fragment. Okay, remember this is 60, right? Maybe it broke off to be H and CH3, CH2, CH2O. Huh. This is worth 60, 15, sorry, this is worth 59. This is worth 1. Of course, there should be a very small peak here. Maybe you just can't see. Okay. Anyway, but that is the whole idea of mass spectrometer. Okay, so it takes a compound, break it into fragments, and these fragments are further analyzed by their mass. Again, this is actually a very good way to check to see if your IR and your HNMR is doing the right thing. So if you think about it, mass spectrometry and IDH are good checkers. Okay, it allows you to check to see if you are right. All right, so I have an example right here. Okay, I have 2-butanol. Okay, and let's draw that for now. And I want you to know, what possible peaks do you think there may be? And you can use, of course, the IB booklet at page 28, which is really just this right here to determine. Okay, so first let's draw T-butanol again. Okay, here's my T-butanol. Very nice. And as I said, they're asking you exactly what would the peaks look like. What peaks would you find? Well, first of all, you will find one peak that you will know for sure. And that peak is 74. Okay? Now, why is 74? Where's the 74? Well, 74 is this whole thing. That whole thing is 74. So you'll find a peak there. Just like you found a peak at 60 here, because 60 represents the whole thing. Right? Okay? Now, the splitting. Where would you find maybe 2 other peaks? Okay? Well, let's just say it will split this and this. Okay. So what would this give you? And what would this give you? Okay. Well, if you look at this page, OH will give you a 17 loss. So what that means is that you're going to have 70 minus 17, which is 57. Okay, so you'll have a peak at 57. Same idea here. If you lost this whole thing, you're looking at 74 minus 45. Okay, so most likely you're gonna get a peak at 29. Okay, so that's 2-terbutanol in terms of its peak. So that's one way, of course, of looking at mass spectrometer. Again, as I said, this is really a way to check to see if you got things right, because the 2 best thing to use is NMR and IR. Okay, whereas mass spec and IHD are more for to see if you're in the right track, if your answer is actually correct. Anyway, I have one big question. And this is my one big question that I want you to look at for today. Since it's Monday, okay, I guess for the rest of the day, you guys can look at this. I have some unknown compound. I have some unknown compound. And I know this unknown compound is C2H4O. Could be anything. Okay, this could be an alcohol. This could be an ether. I think it can be an ether. No, actually, it cannot be an ether. Well, you know what? It could be anything. Okay, it could be anything. What I want you to do is that I want you to calculate the IHD. Okay, and I gave you the IR graph. I gave you the HNMR graph. And I even gave you peaks of what you expect in an MS graph. Oh, look. This should be expected, right? 44, because that's the molar mass of this guy. Well, what are these? What does a fragment 2? If I were to make prediction out of these two and draw that prediction and fragment it, then of course these should make sense. And counting the number of double bond is also makes sense with this. Or maybe a ring. I doubt it's going to be a ring. This can never be a ring. Okay. Alright. So I'll leave that up to you. Once you're done, I want you to write your answer on the comment. Okay? Sometime tomorrow, I guess, I will tell you what the answer is to see if you got it right. Of course, I know what the answer is. I'm not going to tell you right now. So, do that for today. Okay? C2H4O, your job, find IDH, look at these peaks, look at this, and tell me what is the main functional group. Look at these hydrogen's environment. Okay? With these two, you should be able to come up with something and fragments it to see if these two numbers make sense and see if you're right. Anyway, try that now. And guess what? We are done with this course. I have nothing else to tell you about this IBSL course. Of course, I'm not done entirely. We will have a test on Wednesday. This will be your last test on organic chemistry. I will tell you exactly what to focus on, okay, tomorrow, so you are all ready on Wednesday. Alright, so work on this, and I'll see you tomorrow.